All right, last thermo lecture. Um, I think that thermo has made me realize I want to teach AP2 again, if I'm being honest, as challenging as remembering all the rules has been. It's actually been pretty enjoyable. I think that it's just genuinely interesting, like you guys have seemed. You all knew everything about the demos that I tried to do and wasn't very good at either. So I'll make sure to get a better pinwheel next time too. So our learning targets for today, because why not have another law of thermodynamics? A lot of jokes come in with the second law as well, so maybe that's a good thing. So I can explain the second law of thermodynamics, and some of you might already know it. I can define entropy, so the second law has to do with entropy. I can explain how entropy and the second law of thermodynamics are related, so we're going to be able to do that. I can define a heat engine and explain how it works, and I can explain the Carnot cycle and the Carnot theorem. I know you want to say Carnot, he's French, you can't. Um, I'm not going to tell you about the dumb joke I made during my thermo final, I'll tell you that in person. Alright, so, second law of thermodynamics. So many thermal processes proceed naturally in one direction, but not the opposite. Those processes are what are called irreversible. So, heat by itself is always going to flow from hot to a cooler object and never the reverse. Although the reverse process would not actually violate the law of thermodynamics because the first law rather, because energy would be conserved. So we just have these things that are irreversible processes. So in order to properly account for that, that's why the second law of thermodynamics was formulated. So Sadie Carnot here, this very dapper fellow, is credited with having formulated the second law of thermodynamics in 1824. So, heat flows, once again, naturally from hot to a cold object and never spontaneously from cold to a hot object. So, when you place a warm cube of iron next to a cool cube of iron, heat is always going to flow from the warm cube to the cool cube until they reach some kind of equilibrium temperature. Heat will not flow the other way because that would make the cool cube even colder and the warm cube even hotter, which violates nature. Okay. So it will never be this other way around because if you have a warm and a cool cube and you try and do cool to warm, you're just gonna get hot and cold instead. This is what you want here, this equilibrium temperature. Okay. Um, so entropy itself, kinetic energy of macroscopic objects, is associated with organized, coordinated motions of many molecules. Uh, Thermodynamics is very different. Heat transfer involves changes in energy of random disordered molecular motion. And so the conversion of mechanical energy into heat involves an increase of randomness or disorder. That energy is conserved, it just means it's no longer usable to actually do work on the system. So entropy is what provides a quantitative measure of that disorder, and the symbol for entropy is S, and its units are J over K. Okay. I don't remember why it's S. There's a reason, and I'll look it up, but I do not remember. So, the total entropy of an isolated system never decreases. So you may have heard, oh, second law of thermodynamics, entropy is always increasing, or chaos is always increasing, disorder is always increasing. So if you have two liquids, like let's say you're putting milk in your coffee or whatever, entropy is increased by mixing and it cannot be reduced. You cannot undo the mixing of two liquids. And so mixing them together is increasing the energy or disorder of the universe. So, an important statement in the law, the second law of thermodynamics, the entropy of an isolated system may increase, it can never decrease. When a system interacts with its surroundings, the total entropy change of the system and the surroundings also can never decrease. When the interaction involves only reversible processes, the total entropy is constant. Okay, so that's the lowest that it could be, is that entropy remains constant, and that's only if something is completely reversible processes. An example of a reversible process would be a phase transition. Um, when there is any irreversible process, the total entropy is going to increase. So once you have an irreversible process in whatever you're doing, that means the entropy is going to increase. So a heat engine is actually really important. I'll have to go look how much AP actually tests this still, but for anyone who is interested in engineering, heat engines are very important. So a heat engine is a thermodynamic system that converts heat into mechanical energy, which can then be used to actually do mechanical work. I don't know why I didn't capitalize this guy's name. So Dennis Papin, so about like 400 years ago almost, he invented the pressure cooker, and he first described three basic components of any heat engine. He said there's a high temperature reservoir, which is at the top here, a low temperature reservoir at the bottom here, and then some kind of engine containing gas or steam. And so what a heat engine will do, how it actually works, is that the high temperature reservoir is going to transfer some amount of heat QH to the engine. And then in that engine, the part of the heat is then going to be transformed into work that can expand the gas, while the rest of the heat is exhausted to the lower temperature reservoir. So one of the really important challenges in engine design was increasing efficiency. So how, for example, do we get more QH out of this and more work that's actually usable out of the engine, and reduce the amount of QL that's exhausted to this lower temperature reservoir here? So with that in mind, that's where Sadi Carnot came involved. He was a French engineer, and he proposed the idealized heat engine, which he called the Carnot engine, that would provide the maximum possible efficiency with still keeping in line with the second law of thermodynamics. So the Carnot engine operates between a high temperature reservoir and a low temperature reservoir at temperatures TH and TL respectively. So the Carnot engine is going to consist of two processes that are reversible and isothermal. So that's from A to B and from C to D. And then you also have two adiabatic processes from B to C and from D to A. This is a clockwise process here, so it's important to note which way these are actually going. So Carnot theorem itself states that no engine that is operating between two temperatures TH and TL can have a greater efficiency than a Carnot engine operating between the same two temperatures. So ideal efficiency is defined as TH minus TL over TH. And this is the ideal efficiency of any heat engine. This is absolutely not on your reference table, and the temperatures need to be in Kelvin, and that is important because you will not get the same ratio otherwise. So if we start taking a look at some questions, I'll make sure especially that I find some questions on AP Classroom about Carnot cycles and Carnot engines, not Carnot cycles, that's a little more advanced, beyond what I just showed you there. But I'll see what they actually ask about because there really aren't a ton of questions, but I don't want you to get like hit with any curveballs. So, which of the following is not true when two systems with unequal temperatures come into contact with one another? So, heat will flow until thermal equilibrium is reached. That is true, so I'm going to cross that out. No net heat flow occurs once thermal equilibrium is reached. That's also true, so I can cross that out. Entropy is reduced during the process. That I fully disagree with because these are systems with unequal temperatures, and therefore the transfer of heat, we know that that is not a reversible process, and therefore entropy is going to be increased because it is irreversible. And then we can double check on D, but the natural flow of heat will be from the warmer system to the colder system, and we know that that is true. So question 2 here, and then I believe we're done with thermo. Look at that. When ice freezes, its molecules become much more structured. Does this break the second law of thermodynamics? First of all, nothing in the universe can break the second law of thermodynamics, so this answer should not even be on your radar, even though it is kind of funny. So let's look at the answers that it actually could be. So no, because the energy of the molecules increased. Well, that really doesn't have anything to do with the second law of thermodynamics. No, because the entropy of the system as a whole, so the ice and the ice environment increased. That one might be good. And then no, because the density of water decreased. That is not true. Just because ice freezes and yes, the density decreases, that has nothing to do with the second law of thermodynamics. And so the entropy of the system as a whole increased because of the ice and ice's environment, okay? And the structure of the molecules as a result. So, we are done with notes on thermodynamics, which I think is kind of cool. So test soon. Don't remember when, but soon-ish. 18th maybe. I don't remember. Doesn't matter. You guys know better than me.